Let's talk about interference as it relates to analytical measurements. Now, as much as we'd like to think that our methods will not suffer from interference, it does occur. And this is especially a concern when the sample originates from outside of the laboratory. It may contain other species than our analyte that affect the signal that we measure. So here we have a sample. It contains our analyte and an interferent. This is the signal from both, and we'll add those together. That will be what we actually measure. Now, let's assume that we're dealing with a concentration-based method. And if that is the case, then we can expand the signal from each of these components into the proportionality constant for the analyte times the analyte concentration plus the proportionality constant for the interferent times the concentration of the interferent. And we can measure each one of these constants by constructing solutions of known concentration of each of these, measuring them, and creating what's called a calibration curve. And in this case, the slope of the calibration curve will be this proportionality constant. And we can use these two values to determine the selectivity coefficient between them. And in this case, we'll put the proportionality constant for the interferent divided by the proportionality constant for the analyte, and that will equal the selectivity coefficient between these two species. So let's do an example that involves determining the selectivity coefficient and then using it to make a determination as to whether determine the maximum amount of interferent we can have in a sample for a given error level we desire. So what is the selectivity coefficient? Well, if we have a method that's giving an arbitrary unit response of 50 to the analyte, and it gives a response of 2 to the interferent, and assuming both of these are at the same concentration, then we can simply substitute in these values. So 2 was the interferent, and 50 was the analyte. Now, if these were at different concentrations, we'd have to go back up to this formula here to determine the K's for that, but since the concentrations are the same, they will divide out in that process. But that is possible to do. Now, if we run this, we should get a selectivity coefficient of 0.04. And this is relatively good. In fact, we want this to be as small as possible because that would indicate that our interferent is not giving much response to the same concentration of analyte. So this is a relatively selective method. Now, if we come down here to our second question, that is, if the analyte concentration is 1 millimolar, and we want no more than 0.5% error from an interferent, how concentrated can the interferent be? Well, we'll just set up a little calculation here. We'll use our KAI, our selectivity coefficient, times the concentration of interferent, and that should be less than or equal to 0.5%, so we'll just convert that to not a percent value, so 0.005, times the concentration of analyte, which in this case is 1 millimolar. So we'll substitute those in. And we'll substitute in our selectivity coefficient. So 0.005 times 1 millimolar. And then over here, so if we just do a little bit of manipulation here, we'll find that the concentration of our interferent, I'm going to just go ahead and write it over here, has to be less than or equal to 0.125 millimolar, which is actually relatively large, and that's pretty much due to the fact that we want a small error. So even though this method is fairly selective, this is surprisingly large of a concentration for the analyte, but that has to do with the small error that we desire. That's the right way of saying that. Now, what are some of the things that could cause interference? Well, we could have a contaminated reagent. Some reagents, they could sit on the shelf, or we ask people to maintain reagent integrity, but instead they've somehow contaminated it, or it could have been a bad batch from the company that made it. It's hard to know. And so if that's the case, if we have an interferent located inside of a reagent, there's a relatively simple way of dealing with that. Now I'm going to write up here a formula that's very similar to this one, but just so that we can see something here. We'll have the signal from the interferent that has resulted from the reagents. Now the nice thing about this type of interferent is that it should be a consistent amount in our measurement, right? Because say we make a solution and we use 100 milliliters of that solution every time we run this analysis, well, there should be the same amount of reagents in every time that we run the analysis. So we could subtract the result of this if we were to measure it. And the way to measure it is with a method blank. Now there's different kinds of blanks, and you may be familiar with putting a cuvette of just water in a UV-Vis instrument and measuring it. And you may recall that as being measuring a blank. Well, that's a different kind of blank. There are different kinds of blanks. A method blank is where you perform every action that you would to the sample, but instead you have a blank. So you take the blank, but now instead of just immediately measuring it, you would do every chemical transformation or every filtering step, whatever the procedure calls for. You do all of those steps to the blank. Then it becomes a method blank. This can be useful when we have, especially when we have reagents that have their own color, an example of UV-Vis, or something like that, because then those will contribute a non-zero amount of absorption. And in those cases, a method blank can be very important. But what this will do is it will measure any contribution that comes from the reagents. And if there are interferences contained in the reagents or effects from them, we'll be able to measure that and then subtract that part of the signal out before continuing on with the analysis. Now, if the interference is in the sample, this is a little harder to deal with. It's also a little bit more likely. Now, if we know the identity of the interferent, it may be possible to separate it from our sample or separate its effects from the sample. What that means is then when we know the identity of the interferent, we could go ahead and isolate that, create a calibration curve for it, perhaps even using a different analytical method than the one that we're using right now, measure that sample's or that interference's concentration, then determine the response factor for it, then we could go back in and measure our analyte. This is a fairly complicated way of dealing with interference, and it's not usually done for one major reason. Usually we do not know the identity of our interferences. It's hard to measure everything inside a sample, especially when we don't exactly know what we could be looking for. So instead, the preferred way of dealing with an interferent is to leave it inside the sample matrix, but pull out our analyte. So devise some separation method. Could be dissolving it in a new solvent. So perhaps complexing it with some organic reagent and then transferring it from an aqueous environment into an organic layer and then measuring just the analyte. And this has multiple advantages, but one of the major ones is that we're going to leave a lot of the sample matrix behind, and then we'll be able to focus on simply the analyte. And that will leave a lot of interference sources in the original solution. The other advantage that we can have with this is it's often a way to concentrate the sample. So if we can pull the sample out from one solution into another, it's possible that the solution that we're pulling it into could be a lower volume. And if that's the case, then we could concentrate our sample, and more concentrated samples are generally easier to measure. And if we do need the sample to be more dilute, it's much easier to add solvent to a sample than it is to take it away. So this is just a little bit about interference and a little bit of how we can deal with it and some of the math behind having an interferent in our sample.